thanks. You're welcome to say, hey, Moser, you forgot something. It's the third. What is it? That's the guy who ran the something in 3 parasecs. Familiar with that quote? Parasecs are not a measure of time, they're a measure of distance. So he ran it in 3 parasecs is like saying, he ran that in 2 meters. What? How long has she been gone? My pathetic cartoon. Should we be worried? I mean, she left a while ago. How long has she been gone? About 30 meters. It makes no sense. And you know it doesn't make sense. But the reason it doesn't make sense, which is the part that we're giving you now, is that the dimensions don't agree with the units. How many of you have seen this exact graphic before? It's frequently copied. I've used it. I'm pretty sure Mrs. Berger uses it. It's pretty widely copied. Accuracy versus precision. Accuracy is being close to correct. Precision is all about the quality of your instruments, and it's about the ability to make repeated measurements that are going to come out the same. If you've used the triple beam balances that we have in here in chemistry, you know that they are precise. They're not accurate. If you switch from one balance to another, you're going to have huge error because they are just not very accurate. But they are precise. They are precision instruments. And you can mass the same sample 5 times, and you should, if you're good, be able to get the same measurement. Now, the gold standard, of course, is to be both accurate and precise. That's what we want. We want to get the correct value, and we want to do so using instruments and in a manner that allows us to repeatedly get the correct value. If you are accurate but not precise, you float all around average, but your margins are pretty wide. And it's difficult then to tell if you're close to correct value. We're typically working in a scenario where we know the correct value, and we can compare our measurements to the correct value. When you're working in the real world, you don't know the actual value. You're trusting your measurements, and that's dicey ground. If you're getting precision in your measurements, you have to be able to compare it again to a known value, or you can't determine that it's inaccurate. And that's generally sloppiness all over the place. So we'll talk about that when we talk about error. So there are 2 major categories of error. This is why we get inaccuracy. There's method error. And in the lab that you did the same measurements with multiple methods. And it would be a miracle if your measurements agreed closely. Sloppiness typically comes up in that lab also. Well, we measured the circumference of the cylinders by pulling a string, but Olivia pulled it this tight and Brandon pulled it this tight, and so it was a little bit different every time we measured it. That's method error. Then there's parallax. So that's where actually the word parasecs comes from, and parasec is an astronomy unit. So I would invite you all to pick an object in the room, hold your thumb out at a distance, and cover the close one eye and cover an object, make an object disappear. It can be your friend's head, it can be the clock, it can be my face. If you'd like to make my face disappear, go ahead. This is your chance. Can be a paper towel dispenser. You close one eye and cover it with your thumb. Now change the eye you've got closed. No, I'm serious. Play along with my reindeer games. I'm not kidding. Thank you. Reindeer games, come on. Does your thumb jump? Yes. When you change the eye that you're covering, your thumb appears to jump, the object becomes visible. Parallax is the difference in the perceived location of an object based on the location of the observer. So in this case, the observers are your 2 eyes, and they're separated by a gap. What's the gap? Probably like 3.5 centimeters, something like that. Pretty small gap. But we still get a fairly significant jump out at arm's length. Some people seem to have a bigger parallax error. It probably depends on how well their eyes work together. I seem to have a really huge parallax error. My eyes don't work very well together. It's okay. I've been looking through microscopes one-eyed my whole life, and I don't care if they say that's wrong. But if you're taking a measurement, if I were to take a measurement on an instrument with one eye closed, and then I forget which one I had closed, and I close the other one, the measurement's going to jump for me. I do some woodworking, and this is the bane of my existence, because I will take a measurement and then come back, and my mark is off. And so I've got a few shelves that are a little bit funky at home because of my parallax issues. Parallax is actually used in astronomy because you can take two observatories situated on planet Earth, and if you know the distance between the two observatories and you're measuring an object out in space, the difference in the observed position of the object can be related mathematically to the difference in the position of the observers, and it gives you the distance to the object. And how they do that? No idea. Way beyond my pay grade. But that's how it's used. And the term parasec comes from that because it's the, let's see, what is it? The amount of deviation in the light received. It has to do with the amount of parallax change in the light observed in 1 second's worth of time or something like that. I don't know. Anyway, it's a unit of distance. The distance the light is, look it up. I don't know. I'm not an astronomer. My degree's in biology. Okay, the other one is instrument error. And this is a big one, especially working in a high school science classroom, because we got some beat up stuff, folks. We got some seriously beat up stuff. And if you look at any of these lovely old veterans of many high school students before you, actually these are pretty good. This must be, we had one box that came over from the old building that was brand new, had never been opened, had been hiding in Mr. Tooby's supply closet for 15 years. They've actually got pretty straight ends. Most of these, the ends are so beaten up that, you know, is that really a full millimeter on the corner? Probably not. It's been worn away from many, many loving or not student hands. One way to fix that when making a measurement, if you know you've got instrumentation that isn't totally top-notch, you can actually, there are some fudges to get around that. You can do things like start at the 10 mark instead of the 0, because you know that that 10 mark isn't going to get worn away. So if you start at the 10 mark and measure everything from there, then you just have to remember to subtract 10 centimeters when you're done, or start at the 1 centimeter mark. That's a way around instrument error. The other thing is just plain old faulty instruments. We do some massing in here, not nearly as much as you did in chemistry, but when we mass objects, you know, if some rotten, ornery sophomore who was bored sat at the side here and dug BBs out of the balance tray on the triple beam, it's not going to balance. I had that happen once, years and years and years ago. It will never balance. And so when you mass whatever it is you're massing, your measurements are going to be off. That's an issue of accuracy. So precision is really down to the limits of the instrument. It has less to do with your skill, though your skill does play a part. And I have a present for you. I'll give you guys this one, and I'll give you guys this one, and I'll give, oh, here's one of the old beat up. Yeah, that's pretty beat up. I'll give you guys that one, but it's heavy. Give you guys that one. And, I know what I need, but I don't have it. There's no sense crying over that. I'll give you guys that one. Take a measurement of the length of your physics book using the instrument you have. And no cheating and trying to look through the painter's tape. Okay, so since some of you just had a 1 meter long green stick with no markings on it whatsoever, And some of you had an actual meter stick with millimeter markings. What do you have, Brandon, using an actual meter stick with markings every millimeter? What'd you get? 26 millimeters? Just 26? How should I record this?
26.0.
26.0 centimeters. Okay, that's answer number 1. What'd you guys get, Jackie and Dustin?
25.8.
25.8. And you're happy with me recording it as 25.8, just like that?
25.85.
25.85. Okay. And Sean's on it. Okay. What you got, sir? Length of the book? 35.5.
35 was our original one, but I did it.
Length of the book? Those are from all the groups that had an actual meter stick. What about my poor suckers who got the 1 meter long green stick? What's your measurement?
We got 27.94%.
Really? How did you do that? Yes, it is. But we're not name calling just yet. 27.94 centimeters. That's astounding, gentlemen. All right, my other green stick group. What you got?
Just go 20.
You're going to go with 20? How do you want me to record that?
20.0.
You want me to record 20.0. Okay. So, I got some questions here. Yes, yes. My big question is, what can you actually record there? So, we talked a little bit while you were doing your lab about the fact that the number of Sig Figs that you have is the number of divisions on the instrument plus 1 place. So on the actual meter sticks, what is the last marking there? 1/10 of a centimeter or a millimeter. So this digit, and I've got all my settings changed, this digit is certain. That is actually marked. You get 1 more uncertainty. And at the level of those millimeter marks, you're not going to be able to do any better than 0.0 or 0 or 5. Is it right on it? Okay, then it's 26.00. Is it maybe a little skosh past it? Then it might be 26.05. Now, oh green stick people, 27.94 centimeters. Talk about manufacturing data. So those green sticks have, what is the last level of marking on those things? 1 meter. They are marked to the meter. So you get 1 more place beyond that. Which means if you say that that is roughly 20 centimeters, roughly 30 centimeters, that's a big enough range. You don't have to go with 0 or 5. You can reasonably do something like, well, I put my hand in, that is a really weird looking hand. I put my hand at the halfway mark, and it's about halfway between my hand and the end. Yeah, I'll call it 0.3. Yeah, I'll call it 0.2. Because I can't say 0.25. That takes me 1 more digit than is allowable. I most certainly can say 0.94. Nor can I say 20.0. I can say 20 centimeters. I can say, 0.2 meters. But I can't go any further than the instrument allows. That's okay. That's why we do it. It's fine. Because you just need the refresher. When you do measurements in this class, and you will do a lot of measurements in your labs here and your construction projects, I want you to pay close attention to the instrument that you're using. When I grade your labs and constructions, your Sig Fig points now come from 2 places. One is that the Sig Figs that you are recording are correct based on the instrument that you were using. 2 is that you follow the Sig Fig rules internally and you know how to treat those measurements that you've got. In chemistry, we do spend a little bit more time on just, this is how many sig figs I'm given, this is how many I'm allowed to keep. But here, I want you to be diligent about making sure you're pulling the right number of sig figs. Question? There is a Sig Fig review that's linked online. If you forget the rules are on pages 17 through 19 of the book, and that's all the stuff that you should look back over. We will not spend much, if any, time on it, because I really want to do some conversions with you, because those are much harder. Tutorial is linked in the plan, and the book's pages are listed there.